Here we're going to be solving some exponential and logarithmic equations, and to do this I'm basically going to essentially have you practically almost kind of use two things, and it's going to be easy. So the first of these is some clever usage of your logarithmic properties. This is stuff that you've covered last lesson. Second is the one-to-one property, which basically means if you've got two things equal, you can set the components equal, like b to the x power equals b to the y power. You know x has to equal y. If log x equals log y, same thing, x has got to equal y. Alright, let's do some examples. Here we've got 36 to the x plus 1 equals 6 to the x plus 6. Now we can almost use our one-to-one property, except that we've got two different bases here, 36 and 6. So, one thing we can do is rewrite using the same base. Here we've got 36. What if we took that 36 and changed it to 6 squared? Then we would have the same base as this 6 over here. Now we've got x plus 6 as an exponent and x plus 1 as the exponent. When we've got these same bases, that means that the exponents are going to have to be equal as well. That's going to give us 2 times x plus 1 equals x plus 6. Again, that's just setting the exponents equal to each other since we have the same base, and solving from there we get x equals 4. Here we've got ln x equals 6. We want to get this x by itself, so what if we used our inverse of the natural log, e, and we took e to the ln and e to the 6. That's going to cancel out our ln, leaving us with x equals e to the 6. Go ahead and do some fancy calculator work there, and that's going to approximately be 403.43. Here we've got 6 plus 2 log 5x equals 18. Well, if we want to get x by itself first, let's go ahead and isolate this whole log 5x. So if we subtract 6, divide by 2, we're going to get log 5x equals 6. Now, since we don't have a base here, we have an assumed base of 10. That's always the case with logs. Now we can change our logarithmic equation to an exponential. That's going to give us 10 to the 6th power equals 5x. Solving from there, we've got x equals 10 to the 6th divided by 5, or 200,000. Next, we've got log base 8 x cubed equals 12. Let's go ahead and use our power rule. Swing that 3 right to the front. That gives us 3 log base 8 x equals 12. Let's isolate the log x by dividing by 3. That gives us log base 8 x equals 4. From there we can use our exponential to logarithmic conversion. That'll give us 8 to the 4th equals x, which would be 4096. Example 5, log base 4x equals log base 4 3 plus log base 4 x minus 2. Here we've got lots of the same bases. Okay, that's good. I do see an addition sign here with the same base. So what if we convert these two terms to 1, switching addition to multiplication? That would give us log base 4x equals log base 4 3 times x minus 2. Now that we've got log 4 equals log 4, we can set x equal to 3x minus 2 by the one-to-one property. Doing that, x equals 3 times x minus 2, we get x equals 3. This equation, we've got 4 to the x power equals 13. Check this out. If we take the log of each side of the equation, giving us log 4 to the x equals log to the 13th, we can use our power rule and pull that x straight to the front. That would give us x log 4 equals log 13. Now, to solve for x, we just need to do some simple division, giving us x equals log 13 divided by log of 4, or approximately 1.85. Example 7, 4 to the 3x minus 1 equals 3 to the 2 minus x. Now we might think of rewriting these with the same base, but I don't see that 4 and 3 have anything in common. I could do 2 squared, but 3, I can't change that to 2, nothing's really going to work there. So, what if we went ahead and took the log of both sides just like last time and used our power rule to bring these guys to the front? Doing that, we'll get 3x minus 1 times log of 4 equals 2 minus x times log of 3. Let's go ahead and just solve from there. What can we do? Well, let's go ahead and distribute everything else out. That gives us 3x log 4 minus log 4 equals 2 log 3 minus x log 3. Continue solving from there. Well, I know we definitely need to get our x's on one side of the equation, so let's go ahead and move our x's to the left and everything else to the right. So I added this x log 3 over and added that log 4 over to the right side. Now we can go ahead and factor out an x here. Factoring that x out in the front, we're left with this whole thing here. Now this is pretty messy, but we've got our x outside of all our logarithms, so why don't we just clean this up a bit using some of our rules. I'm going to put this 3 using the power rule back here, giving me 4 cubed. I've also got this log 3 over here. I know I can multiply those, so this whole thing is going to turn into x log 4 cubed times 3. And why not the same thing over here? We can take our 2, put it right up here to make it 3 squared, plus log of 4. We've got the same automatic base of 10. That gives us log 3 squared times 4. Alright, let's continue simplifying this out. Multiplying that out, we get 4 cubed times 3, 192. 3 squared times 4 is 36. Let's divide that log 192, giving us our final answer, if we plug that into a calculator, of 0.68. I've been working very hard to protect you from something, but I think you're old enough now. Extraneous solutions, they do exist, and they are dangerous because when we solve these logarithmic equations, sometimes we get solutions that don't make sense. Always check if your answer makes sense. We haven't been doing that because we've been trying to go through these quickly, but we always need to make sure it works with our original equation. One way to check is to plug it in your calculator, and if you get an error message, of course, that means it doesn't work. But essentially, whenever we have a logarithm equation, we cannot plug in a negative value for x. So if you ever get a log such that your log value in here is negative, that's not going to work. That's an extraneous solution. Negative values are not in the domain of logarithmic functions. Let's do one such example just so you're not caught off guard when it happens to you. We've got log base 12 12x plus log base 12 x minus 1 equals 2. Well, I've got the same log base here, so let's change this addition into multiplication. That gives us log base 12 12x times x minus 1 equals 2. Simplifying that out a little, we get log base 12 12x squared minus 12x, distributing here. Then we can use our converting the logarithmic to exponential. 12 to the second power equals 12x squared minus 12x. From there, let's just go ahead and solve like a normal quadratic. Doing that, we get 12 squared, 144, subtract that over. We're going to get 12x squared minus 12x minus 144 equals 0. We can factor that out or use the quadratic formula, and we're going to get answers of x equals 4 and negative 3. But we do need to check for those deceptive extraneous solutions. So let's go ahead and take these, plug them in, and see what we get. First, let's plug in 4 for each x. That gives us log base 4 of 12 times 4 plus log base 12 of 4 minus 1 equals 2. If we work all of that out, we're going to end up getting a true answer. We're just going to get log base 12 of 144 equals 2, which is correct. No errors, no negative logarithms. This solution is good. Now let's try this negative 3 on for size. Let's plug that in. That gives us log base 12 12 times negative 3 plus log base 12 negative 3 minus 1 equals 2. And we actually end up with log base 12 of negative 36 and a log base 12 of negative 4 over here. If you plug those into your calculator, or just know you can't have a negative logarithm, this guy is extraneous. So we are left with x equals 4 as our only answer. You may be asking yourself, how am I going to ever know what to do when I see these equations on my own? They make sense, but I don't know when to do what. And the answer to that is basically just practice through them. There's only so many ways you can solve these types of equations. You'll get better and better as you go. Just remember your properties of equality and try to use the examples we've done in this video as a guide. I know you can do it. Let me know if you need any help.